Good morning. Today we are going to start our next chapter, and the chapter's name is Automorphism and Galois theory. Okay, so uh, first section is Automorphism of fields. The definition of automorphism. Now, what do you mean by an automorphism? Automorphism is what is an isomorphism? An isomorphism in groups. What is an isomorphism? Or in rings? Suppose phi is a map from R to R dash or ring R to R dash. Then phi is called an isomorphism if phi satisfies the following properties. Phi is 1 to 1, phi is on to, and also satisfies phi of alpha plus beta equal to phi of alpha plus phi of beta, and phi of alpha beta is equal to phi of alpha into phi of beta. Okay. Now automorphism means this domain and range must be equal. Actually, domain and codomain must be same. Okay. Phi from some R to R is called an automorphism if it satisfies these properties. As an isomorphism from same set to itself is called an automorphism. We will discuss it, about this later. Okay. Before this, we are going to discuss some definitions. Now, the first definition is, listen carefully, each term is very important. Let E be an algebraic extension of the field F. Okay. E is an algebraic extension. Now, what is the meaning of that? Every element alpha belongs to E is algebraic over F. Now, every element alpha belongs to E is algebraic over F means, recall your theorem. That means there exists a polynomial which satisfies algebraic over there exists a polynomial f such that f of alpha equal to 0. In that case, you have already discussed there exists an irreducible polynomial, and this is about irreducible of alpha over f. This already you know. Okay. So, let E be an algebraic extension of elements. Okay. Algebraic extension of the field F. Now, two elements alpha comma beta belongs to E are conjugate over F. Two elements alpha comma beta belongs to E are conjugate over F if irreducible of alpha over F equal to irreducible of beta over F. These are exist because by this comment, that is E is an algebraic extension. So for any alpha belongs to E is algebraic over F, therefore irreducible, the theorem. Just recall our previous theorems. Okay, so if there exist two elements alpha and beta, and they are conjugate over F if irreducible of alpha over F is equal to irreducible beta over F. That is, alpha and beta are zeros of same irreducible polynomial over F. Hope the definition is clear. Okay. Now moving to one problem, one example. Prove that root 2 and minus root 2 are conjugate over Q. Okay. If you consider the polynomial x square minus 2, clearly root 2. Okay. Root 2 square minus 2 equal to 2 minus 2 which is equal to 0. So root 2 is a 0 of this polynomial. Similarly, if you take minus root 2 square minus 2, this is same as 2 minus 2 which is equal to 0. So are zeros of x square minus 2. And clearly this is an irreducible polynomial over Q. Therefore, root 2 and minus root 2 are, sorry, this is not irreducible. They are conjugate over Q. Okay. Now let A comma B belongs to R, B not equal. Show that A plus IB and A minus IB are conjugate over R. Okay. So what we have to prove? We have to prove irreducible of, we have to prove irreducible of a plus I beta over r is same as irreducible of a minus I beta over r. For this, we are considering the polynomial x square minus 2ax plus a square plus b square. Why we are considering this? We are starting with, actually we are starting with some x is equal to or alpha equal to a plus ib, or x is equal to a plus ib. So x minus a equal to ib, x minus a whole square equal to ib square, that is x square minus 2ax plus a square equal to minus b square, that is x square minus 2ax plus a square plus b square equal to 0. Therefore, if we take x is equal to a plus ib, we get this polynomial. Therefore, clearly a plus ib is the root of this polynomial. Okay, or if you write root of this polynomial, this quadratic equation, what about the root? What about the root? Minus a minus b plus or minus b plus or minus root of b square minus 4ac divided by 2a. This is our definition, and this is the root. Okay, so here for minus b we have minus 2a, that is plus or minus root of 2a square is 4a square minus 4a. For a means here 1, c means a square plus b square divided by 2a. 2a means here 2. So this is 2a plus or minus root of 4a square minus 4a square minus 4b square. So minus 4a square, 4a square cancel. This is minus 4b square divided by 2. That is 2a plus or minus 2bi by 2. This cancel, we get a plus or minus bi. So a plus bi and a minus bi are root of this polynomial. Okay, that's here. So consider the polynomial x square minus 2ax plus s square plus b square. Roots of f of x are of the form this one, and which is equal to a plus ib. So a plus ib and a minus ib are zeros of this polynomial, and clearly this is an irreducible polynomial over r of x. Okay, if this is reducible, that means this polynomial has a 0 in R. But this, because it is a polynomial of degree 2, any polynomial of degree 2 is reducible if it has a factor. Okay, we can factorize this linear fact product. Okay, one linear factor must be there. That means it has a 0 in R because it is over R of x. But roots of this are this one, clearly they are not belongs to R. Therefore, this is an irreducible polynomial, and thus we get a plus ib, and a plus ib and a minus ib are root of same irreducible polynomial. Therefore, a plus ib and a minus ib are conjugates over R. Okay. Now, moving to next theorem, conjugation isomorphism theorem. This is very important theorem, and proof is also important. Statement is also we are using in our next classes too. So moving to statement. Let F be a field. Clear? And let alpha and beta be algebraic over F with the degree of alpha over F equal to n. Okay, let F be a field and let alpha and beta be algebraic over F with the degree of alpha over F equal to n. Clear? Then the map, we are defining a map psi alpha beta. Okay, as alpha and beta are algebraic over F, clearly we can define f of alpha. And already in previous classes we have proved elements of f of alpha are of the form, if it is of degree n, then elements are of the form b0 plus b1 alpha plus etc plus bn minus 1 alpha raised to n minus 1, and expression is unique. We have already discussed this result. Okay, so here we are defining a map psi alpha beta from f of alpha to f of beta. F of alpha means elements are of this form. F of beta means elements are for alpha. You can replace it as beta, or bi is also belongs to F. And the map is defined by psi alpha beta of elements of f of alpha. You take here, we are taking c naught plus c1 alpha plus etc plus cn minus 1 alpha raised to n minus 1 equal to c naught plus alpha. You are replacing by beta, c1 alpha beta plus c2 beta square plus etc cn minus 1 beta raised to n minus 1. Ci belongs to f is an isomorphism of f of alpha onto f of beta if and only if alpha and beta are conjugates over f. So the conjugation isomorphism theorem says that psi alpha beta is an isomorphism from f of alpha onto f of beta if and only if alpha and beta are conjugates over f. Okay, so for defining f of alpha and f of beta, we must have alpha and beta is algebraic over f, and degree of alpha over f equal to n, that then it will be of cn minus 1 alpha raised to n minus 1. Okay, elements. Okay, so psi alpha beta is an isomorphism from f of alpha onto f of beta if and only if alpha and beta are conjugates over f. Clear? Hope this statement is clear. Once again, I am repeating the statement. Let F be a field and let alpha and beta be algebraic over F with degree of alpha over F is equal to N. Okay, then the map psi alpha beta from f of alpha to f of beta defined by psi of alpha beta of c naught plus c1 alpha plus c2 alpha square plus etc plus cn minus 1 alpha raised to n minus 1 is equal to. You are just changing alpha as the output is c naught, changing alpha as beta. C naught plus C1 beta plus C2 beta square plus etc plus Cn minus 1 beta raised to n minus 1. Ci belongs to F, and that is an isomorphism of f of alpha onto f of beta if and only if alpha and beta are conjugate over F. Hope the statement is clear. So we are proving the first part is, we suppose that psi alpha beta is an isomorphism, then we are proving alpha and beta are conjugate over F. Conversely, we assume that alpha and beta are conjugate over F, and we are proving psi alpha beta defined like this is an isomorphism. Okay. So, moving to the proof, suppose that psi alpha beta from f of alpha to f of beta defined like this, okay, is an isomorphism, okay. And as alpha and beta are algebraic over f, clearly irreducible of alpha over f exists. Let f of x equal to irreducible of alpha over f, and let this polynomial be a naught plus a1x plus etc plus an x raised to n, because it is of degree n. Okay, then it is an irreducible of alpha over f means clearly alpha must be a root of irreducible of alpha over f, because it is the smallest polynomial having alpha as a root. That means f of alpha must be equal to 0. So what is f of alpha? You replace x by alpha. So a naught plus a1 alpha plus a2 alpha square plus etc. an alpha raised to n equal to 0. Clear? Now psi alpha beta is an isomorphism. As an isomorphism, but we know that psi of is isomorphism means 1 to 1. Okay. So psi of alpha beta of 0 must be equal to 0. Okay, psi alpha beta of 0 equal to 0. For the left side 0, we are replacing this 0 by a naught plus a1 alpha plus etc plus an alpha raised to n, which is equal to 0. Now you take psi out, psi inside. By definition, psi of alpha beta of a naught and psi of alpha etc like this, a naught plus a1 beta plus etc plus a2 beta square plus etc plus an beta raised to n must be equal to 0. Okay. So beta is a root of a naught plus a1x plus etc plus an x raised to n. Here you may have confusion how psi alpha beta of an alpha raised to n an alpha raised to n. Here already we have this element, then how this is possible? Okay, in that case you can write this as an psi alpha beta of alpha into alpha raised to n minus 1, and this is an psi alpha beta of alpha psi alpha beta of alpha raised to n minus 1, and this is an high alpha beta of alpha is alpha beta, and this is beta raised to n minus 1, and that is an beta raised to n. Okay, so you can we get psi alpha beta of this one equal to this one. This implies this is equal to 0. That means beta is a root of a naught plus a1x plus etc plus an x raised to n. And but we know that irreducible of beta over f. That means beta is a root of beside a root of f of x. Okay, but we know that irreducible of beta over f is the smallest polynomial having beta as a root. And here beta is a root of f of x means this irreducible of beta over f must divide f of x. That is irreducible of beta over f must divide irreducible of alpha over f. So here we started with the irreducible alpha over f. If we started with the irreducible of beta over f, and psi alpha beta is an isomorphism. Therefore, it is 1 1 and on 2, and its inverse exists. Psi alpha beta inverse you can write as psi beta alpha. Okay, so if we started with the irreducible of beta over f and apply psi beta alpha, then clearly we get irreducible of beta alpha over f divides irreducible of beta over f. Here if we start with this, then we get this one, and this means irreducible of beta over f divides irreducible alpha over f. But for the next part, we started with irreducible of beta over f. Let f of x equal to irreducible of beta over f, and let it be a naught plus etc plus etc. Or you can choose any polynomial. Okay, that means irreducible of a naught plus, that means a naught plus a1 beta plus etc plus beta raised to n. As psi beta alpha is an isomorphism, psi beta of 0 beta alpha of 0 equal to 0. So in case beta of alpha means first apply, and this is equal to, finally you get a naught plus a1 alpha plus a2 beta alpha square plus etc. That means irreducible of beta over alpha over f divides irreducible of beta over f. Okay, so what we get x divides y and y divides x. Also both polynomials are monic polynomial. That means x divides y divides x implies we get x equal to y. That means irreducible of alpha over f equal to irreducible of beta over f, because polynomial degree of polynomials are more coefficients are. Okay, we have x divides y and y divides x. Okay, so here also each polynomial are monic polynomial, and we get irreducible of alpha over f must be equal to irreducible of beta over f. Okay, therefore alpha and beta are conjugates over f. Reducible alpha over f equal to irreducible of beta over f means alpha and beta are conjugate over f. Now conversely, suppose that alpha and beta are conjugate over f, and we have to prove that there exists a isomorphism defined like this, or psi alpha beta defined like this is a isomorphism. Okay. So suppose irreducible of alpha over f equal to irreducible of beta over f, and let it be p of x. Then the evaluation homomorphism phi alpha from f of x to f of alpha, and consider the evaluation homomorphism phi beta from f of x to f of beta. Both have same kernel ideal generated by p of x, because we have already discussed. Okay, kernel of this evaluation homomorphism is actually ideal generated by p of x. So by fundamental homomorphism corresponding to phi of alpha, by fundamental homomorphism theorem corresponding to phi of alpha from f of x to f of alpha, there is a natural homomorphism psi alpha mapping f of x over ideal generated by p of x onto phi alpha of f of x. Okay, just go through fundamental homomorphism theorem. So given phi, there exists a psi which map from f of x to over ideal kernel p of x to image of phi alpha of f of x. And phi alpha of f alpha is algebraic over f. Phi alpha of f of x is same as f of alpha. Similarly, psi phi beta gives an isomorphism psi beta mapping f of x over ideal generated by p of x onto f of beta. So we have like this. We have f of x to f of beta, we have phi beta, and f of x to f of alpha, we have phi alpha. And here f of x to ideal generated by p of x to psi alpha, and here we have psi beta. This is an isomorphism, this is an isomorphism, this is an isomorphism. So if we consider psi beta composition, psi alpha inverse, then clearly it is an isomorphism from f of alpha to f of beta, because this is an isomorphism, this is an isomorphism, 1 1 on 2. So composition also 1 1 on 2, and psi beta composition psi alpha inverse is a map from f of alpha to f of beta. Okay. So so we are defining psi beta composition psi alpha inverses psi alpha beta. Psi beta composition psi alpha inverses psi alpha beta, and psi alpha inverse from this one, and psi beta for this composition is also from this. Okay. So his composition of two isomorphism is again an isomorphism. Psi alpha beta is an isomorphism from f of alpha onto f of beta. Now what we have to prove? We have to check whether psi alpha beta is defined as in the statement. Okay. So for this one, C naught plus C1 alpha etc. belongs to f of alpha. We have psi alpha beta of C naught plus C1 alpha plus etc. plus C n minus 1 alpha raised to n minus 1 is equal to psi alpha beta is psi beta psi alpha inverse of this one. Okay, and this is psi alpha beta of, what is psi alpha inverse of this one? Actually psi alpha is a map. How we are defining psi alpha? Psi alpha is a map from f of x to ideal generated by p of x to f of alpha. How we are defining? We are defining psi alpha of element of f of x, some polynomial a naught plus a1x plus a2x square plus, suppose I am writing of degree 2 plus ideal generated by p of x is equal to a naught plus a1 alpha plus a2 alpha square. You can look at this theorem and using the part from Kroneker's theorem. You can get if alpha takes some x plus ideal generated by p of x to map goes to alpha plus alpha. Okay, so x, that is x plus ideal generated by p of x must goes to, or alpha maps to this one, or this goes to alpha. So this one. So psi alpha inverse of a naught plus a1 alpha plus a2 alpha square is same as a naught plus here c naught plus c1x plus etc. c n minus 1 x raised to n minus 1 plus ideal generated by p of x. And if we apply beta, psi beta, and this is equal to c naught plus c1 beta plus etc. plus c n minus 1 beta raised to n minus 1. Thus, psi alpha beta is the map defined as in the statement of the theorem, and psi alpha beta is the map from f of alpha onto f of beta, and this is also an isomorphism. Okay, that's the conjugation isomorphism theorem. So for the first part, you have to just know the definition of the irreducible alpha and beta. And for the second part, you must know what is the natural, how we are defining psi alpha, okay, and psi beta. Okay, that's